Welcome to Lesson 5.1 Doppelpunkt Understanding Chat Models. Overview. Warby, the chat models aren't just language models with a friendly interface bolted on. They're architecturally the same as base models, but trained differently, formatted differently, and designed for a fundamentally different purpose. Understanding those differences is what separates someone who can run a fine-tuning script from someone who actually knows what they're building. That's what this lesson is about. Plan for about 45 minutes and expect to come out the other side with a solid mental model of how chat systems actually work under the hood. Learning objectives. By the end of this lesson, you'll understand exactly how chat models differ from base models, what instruction tuning and RLHF actually do to a model's weights and behavior, how chat templates work, and why different models use different formats, how system prompts steer model behavior throughout a conversation, how multi-turn conversations are structured and passed to the model, and how context windows constrain everything. These aren't just concepts to memorize. Every one of them will directly affect decisions you make when fine-tuning your own model. Base model versus chat model. A base model has one job: predict the next token. That's it. It's trained on a massive corpus: books, websites, code, academic papers, and it gets extraordinarily good at continuing text. Give it a sentence and it will complete it. Give it a question and it might just keep asking more questions. There's no concept of answering or helping. It's a statistical text completion engine, and a brilliant one. Here's what that looks like in practice. If you feed a base model the prompt, "the capital of France is," it will output something like Paris, a city renowned for its art, culture, and the iconic Eiffel Tower. Notice what happened. It didn't answer a question. It completed a sentence. The model has no awareness that you were asking anything. It just recognized the pattern and continued it. That's the key distinction to hold in your mind as we move forward. A chat model starts as a base model, then gets trained further, first on instruction datasets and optionally through reinforcement learning from human feedback. The result is a model that understands the difference between a question and an answer, between a request and a response. Feed it "what is the capital of France?" and it will tell you the capital of France is Paris. It's not just completing text anymore, it's responding to intent. That single behavioral shift from text completion to intent response is what makes chat models useful for building real applications. The underlying transformer architecture is identical to the base model. What changed is the training data and the training objective. The model learned through thousands of examples that when a user asks a question, the correct behavior is to answer it clearly and directly. That learned behavior is what you're going to be fine-tuning and extending. Here's the full picture side by side. Base models are trained purely on text prediction, accept raw text as input, produce continuations as output, follow instructions poorly, and have no concept of conversation history. Chat models add instruction tuning on top of that foundation. They expect input in a structured chat template format, produce helpful responses rather than continuations, follow instructions reliably, and maintain awareness across multiple turns. The use case split is clean. Base models for text completion tasks, chat models for assistance and interactive applications. How chat models are created. The journey starts with pre-training. You take a massive text corpus. We're talking trillions of tokens scraped from the internet, digitized books, code repositories, scientific papers, and you train a neural network to predict the next token at every position. This is computationally enormous, takes weeks on thousands of GPUs, and produces what we call a base model. Llama 33B is a base model. At this stage, the model has absorbed an extraordinary amount of world knowledge and linguistic structure, but it has no idea how to have a conversation. It's like someone who has read every book in a library but has never spoken to another person. The next step is supervised fine-tuning, or SFT. You take that base model and train it further on a curated dataset of instruction response space. Thousands of examples where a human asked something and a human expert wrote the ideal answer. The model's weights get updated to favor this new pattern. Question in, helpful answer out. The output of this process is what's called an instruct model. Llama 3.3b instruct, for example. This is the stage where most practical fine-tuning happens, including everything you'll be doing in this course. You're not training from scratch. You're steering an already capable model toward a specific behavior. The instruction dataset that drives SFT is structured as conversations. Each training example is a JSON object containing a list of messages, where each message has a role, either user or an, and the actual text content. This format is deliberate. It teaches the model that conversation has structure, that turns alternate between participants, and that the assistant's job is to respond to what the user said. When you later create your own fine-tuning dataset, you'll be building files that look exactly like this. Optionally, after SFT, some models go through a third stage, reinforcement learning from human feedback, or RLHF. Here, the model generates multiple candidate responses to a prompt. Human raters rank those responses from best to worst, and those rankings are used as a training signal to push the model toward producing higher quality outputs. This is how models like GPT-4 and Claude achieve their polished, helpful, and safety-conscious behavior. It's expensive. You need a lot of human annotators and significant compute, which is why most fine-tuning projects, including ours, stop at SFT. What RLHF actually improves is nuanced. Response quality goes up, the model gets better at refusing harmful requests, it becomes more consistently polite and helpful, and its outputs align more closely with human preferences rather than just statistical likelihood. These are real, measurable improvements, but they come at a cost that's out of reach for most teams. For our purposes, SFT will get us very far. Chat format anatomy. Every conversation you send to a chat model has the same underlying structure, a list of messages, each tagged with a role. The system role appears once at the top and sets the model's behavior for the entire conversation. The user role carries what the human typed. The ans role carries what the model previously responded and crucially what you want the model to learn to generate during training. In this example, the system says, "You are a helpful assistant." The user asks, "What is 2 plus 2?" and the assistant responds, 2 plus 2 equals 4. Simple, but this three-part structure is the foundation of everything. The system message is your primary lever for controlling model behavior. It runs once at the start of the conversation, and its influence persists through every subsequent turn. Think of it as the briefing you give an employee before they get on a customer call. You set the role, the tone, the constraints, and the expectations all at once. The range of what system prompts can do is wide. You might tell the model it's a coding assistant that only writes Python, or a customer support agent for a specific product, or a professional translator that always responds in formal register. Each of those prompts fundamentally changes how the model interprets every user message that follows. The model doesn't have a fixed personality. The system prompt is where personality gets defined per conversation, per application. User messages are straightforward. They carry whatever the human typed. But it's worth noting that user doesn't have to mean a literal human at a keyboard. In automated pipelines, the user role often carries programmatically generated prompts. The model doesn't know or care. It sees a role label and content and responds accordingly. User messages can be anything. Open-ended questions like "What is Python?" Concrete task requests like write a function to sort a list, or structured inputs like translate hello, how are you, into Spanish. The model handles all of these through the same mechanism. It reads the conversation history, including the system prompt, processes the user turn, and generates the assistant response. The variety of inputs is what makes chat models so flexible. Assistant messages are what the model generates, and during fine-tuning, they're what the model is trained to produce. This is the critical distinction. When you build a training dataset, the assistant turns are the ground truth. The model will learn to generate responses that match those examples. Everything else in the conversation, system prompt, user messages, is input context. The assistant turn is the target. Assistant responses can range from a single sentence to multi-paragraph explanations with code. In a training dataset, you might have an assistant turn that introduces Python as a high-level, interpreted programming language, concise and accurate, or one that provides a working sort function with a brief explanation, or one that delivers a translation with a note about regional dialect differences. The quality of these assistant turns in your training data directly determines the quality of your fine-tuned model. Garbage in, garbage out, but also excellence in, excellence out. Here's a complete single turn example. The system message establishes the assistant's helpful role. The user asks, "What is artificial intelligence?" The assistant responds with a clear, accurate definition. When you feed this structure into a fine-tuning run, the model sees the system and user messages as input context and learns to generate the assistant response as output. One example like this doesn't teach the model much. 10,000 examples like this, covering diverse topics with high-quality responses, teaches the model a great deal. Multi-turn conversations follow the exact same structure. You just add more message objects to the array. The system message stays at the top. Then user and assistant turns alternate. In this example, the user asks about AI, gets an answer, then asks for a specific example and gets another answer. The model receives the entire message array as input each time, which means it has full access to everything said so far. That's how it maintains context, not through any special memory mechanism, but simply because the whole conversation history is in the input. Chat templates. Here's something that trips up a lot of people. The JSON messages format we've been discussing is a convenient abstraction for humans. The model itself never sees JSON. Before the conversation reaches the model, a chat template converts that structured list of messages into a single flat string of text with special tokens marking where each role begins and ends. Different model families use completely different templates. Using the wrong template on a model is one of the most common sources of silent, hard to debug performance problems. Start with this familiar JSON structure: a system message, a user greeting, and an assistant response. This is the human-readable representation of the conversation. The chat template's job is to serialize this into the exact string format the model was trained to expect, including all the special tokens that signal role boundaries. After the Llama 3 chat template processes that JSON, the output is a precisely formatted string. It begins with the special begin of text token, followed by header tokens that announce the system role, then the system message content, then an end of turn token. The same pattern repeats for the user turn and again for the assistant turn. Every token in this sequence has meaning. The model was trained to recognize these boundaries and use them to understand who is speaking and when a turn ends. The special tokens in Llama 3's template each serve a specific purpose. The begin of text token marks the absolute start of the input. The start header and end header tokens wrap the role name, system, user, or us, creating a clear label for each turn. The end of turn token signals that a speaker has finished. These aren't arbitrary. They're the tokens the model saw during its own training, and the model has learned to condition its behavior on them. Use different tokens, and the model gets confused. When you apply the template to a conversation that ends with the user's turn, notice what appears at the end of the output: the assistant header tokens, but no content yet. That empty assistant turn is intentional. It's the generation prompt. The model sees the full conversation up to that point, sees the assistant header indicating it's now the assistant's turn to speak, and begins generating. That's the moment inference happens. Here's how this works in code with unsloss. After importing fast language model and loading llama-3.2-3b-instruct with a max sequence length of 2048 and 4-bit quantization, you call the tokenizer's apply_chat_template method, passing that final flag is what appends the empty assistant header at the end, signaling to the model that it should start generating. The output of apply_chat_template is the raw string you'd see in the formatted template, exactly what gets tokenized and fed into the model. The formatted output confirms everything is structured correctly. You'll see the begin of text token at the very start, then the system header and content, then the user header with the question "What is AI?", then the end of turn token, and finally the assistant header with no content. That's where the model picks up and starts generating its response. If this output looks malformed, or the tokens are in the wrong order, that's your signal that something went wrong with template application before you ever run inference. That empty assistant turn at the end isn't a bug or an oversight, it's the mechanism. The model generates text by predicting what comes next, and what comes next after the assistant header is the assistant's response. Remove that header, and the model doesn't know it's supposed to speak. Context window and memory. Every transformer model has a hard limit on how many tokens it can process in a single forward pass. This is the context window. For llama-3.2-3b, the default context window is 8,192 tokens. That's the total budget for everything: the system prompt, the entire conversation history, and the response the model is about to generate. With rope scaling, this can be extended to 128,000 tokens, but that comes with memory and compute trade-offs. For most fine-tuning work, the default 8,192 is your working constraint. The context window isn't just a limit on the current message, it's a limit on the entire conversation that the model can see at once. Every time the user sends a new message, your application concatenates the system prompt, every prior user and assistant turn, and the new user message, then feeds the whole thing to the model. The model has no persistent memory between calls. Its only memory is whatever fits in the context window right now. Here's a concrete example of token budgeting. Suppose your system prompt consumes 50 tokens, the user's message takes 30 tokens, and the assistant's response uses 420 tokens. That's 500 tokens total, well within an 192 token window. As conversations grow longer, those numbers accumulate. A 20-turn conversation with detailed responses can easily push past 4,000 tokens. Once you exceed the context window, something has to give, and that something is usually the oldest messages in the conversation. When conversations exceed the context window, you have 4 options. Truncation drops the oldest messages. Simple, but the model loses early context. Summarization compresses the conversation history into a shorter representation before it's included, preserves information but adds complexity. A sliding window keeps only the most recent end turns, predictable behavior, easy to implement. Or you can simply reject inputs that are too long and return an error. appropriate for some APIs where you want strict guarantees. Which strategy is right depends entirely on your application. Here's a practical implementation of the truncation strategy. The truncate_conversation function takes a list of messages and a token limit, then rebuilds the conversation in two passes. First, it extracts and preserves the system message. You almost never want to drop that, since it defines the model's behavior. Then it takes the last 10 non-system messages, ensuring the most recent context is what survives. The result is a trimmed message list that fits within your token budget. In production, you'd want to make the window size dynamic based on actual token counts, but this pattern is the right starting point. System prompt engineering. The system prompt is the most powerful tool you have for shaping model behavior without touching any weights. It runs once at the start of every conversation and influences every response that follows. Getting it right is part craft, part engineering, and it matters enormously for fine-tuning because the system prompts in your training data teach the model what to expect at inference time. The most basic system prompt establishes a role. You are a helpful AI assistant. It's minimal, but it's not nothing. It tells the model to orient toward being useful rather than, say, continuing text in a narrative style. This is your baseline. Every more specific system prompt builds on this foundation by adding constraints, personality, output format requirements, or domain expertise. A more targeted system prompt might read, "You are an expert Python programmer. Always provide clear working code examples with explanations." Now you've done two things: established domain expertise and specified output format. The model will lean toward Python solutions, include runnable code, and add explanatory text. You haven't changed any weights. You've just given the model a clear behavioral contract to follow. Persona-driven system prompts go further. You are a friendly and enthusiastic science teacher who loves making complex topics accessible to beginners. This shapes not just what the model says, but how it says it, the vocabulary it chooses, the analogies it reaches for, the level of assumed background knowledge. Persona prompts are particularly effective when fine-tuning for customer-facing applications where tone consistency matters. Customer support prompts add behavioral constraints. You are a polite and professional customer support agent. Always end your responses with, "Is there anything else I can help you with?" That closing question isn't just a nicety, it's a measurable consistency requirement. If your fine-tuned model reliably includes that phrase, you know the training data and system prompt are working together correctly. For structured data extraction, the system prompt can enforce output format directly. You are a data extraction assistant. Always respond in valid JSON format. This is one of the most powerful uses of system prompts, constraining the model's output to a machine parsable format. When you fine-tune on examples that pair this system prompt with JSON formatted assistant responses, the model learns to produce consistent parsable output reliably. A few hard-won rules for system prompt design. Do be specific about the role. Define the output format explicitly. Set tone and personality clearly. Include any important constraints and keep the whole thing under 200 tokens to preserve context budget. Don't write a novel. Long system prompts waste tokens and often confuse rather than guide. Don't be vague. Be helpful tells the model nothing it doesn't already know. Don't contradict what the model learned during training, and don't over-constrain. If you pile on too many rules, the model will struggle to satisfy all of them simultaneously. Testing chat format. Here's a complete test harness for verifying that your chat setup works correctly before you commit to a full fine-tuning run. The code loads llama-3.2-3b-instruct with unsloth, max sequence length 2048, 4-bit quantization, then defines a test_chat function that handles the full pipeline. Apply the chat template with add_generation_prompt set to true, tokenize the result, run model.generate with a temperature of 0.7 and a max of 200 new tokens, decode the output, and extract just the assistance portion of the response. 3 test cases exercise different scenarios: a single-turn question, a multi-turn dialogue where the second user message builds on the first, and a personality-driven interaction using a custom system prompt. Run all 3 and compare the outputs. If the model is tracking conversation context and respecting the system prompt, your setup is solid. Chat model evaluation. Evaluating a chat model response isn't just about checking whether the answer is factually correct. A good response has to clear 6 bars simultaneously. It must be relevant, actually answering what was asked. It must be coherent, grammatically and logically sound. It must be consistent, matching the personality and tone established in the system prompt. It must be contextual, acknowledging and building on the conversation history. It must be helpful, genuinely useful to the person asking, and it must be safe, free from harmful, offensive, or inappropriate content. These 6 criteria are your evaluation rubric for both manual testing and automated quality checks. Breaking that rubric down into a practical checklist gives you a systematic way to audit model outputs. Under relevance, does the response directly address the query, stay on topic, and honor any explicit instructions? Under coherence, is the grammar correct? Is the logic sound? Are there any internal contradictions? Context awareness, does the model remember what was said earlier in the conversation and maintain a consistent thread? Personality, does the tone match the system prompt and stay consistent across turns? Helpfulness, does the response provide enough detail and does it suggest follow-ups where appropriate? Safety, is the content free from harm and does it respect user boundaries? Running this checklist on a sample of outputs before and after fine-tuning is how you measure whether your training actually improved the model. Key concept summary. Wind a summary. See me see 3 techniques quickly. The full pipeline from raw model to production chat assistant has 3 stages. Stage 1 is the base model, a text prediction engine trained on trillions of tokens, excellent at language, poor at following instructions. Stage 2 is instruction fine-tuning, supervised training on instruction response pairs that teaches the model to respond helpfully to user requests. Stage 3 optional is RLHF or DPO, preference optimization using human feedback that pushes response quality, safety, and alignment further. Each stage builds on the previous one. You don't retrain from scratch at each step, you refine. And for most fine-tuning projects, stage 2 is where you'll spend your time. 3 concepts anchor everything in this lesson. First, the messages format. Every conversation is a structured list with system, user, and assistant roles, and that structure is what your training data must follow. Second, chat templates, the mechanism that converts that human-readable JSON into the model-specific token sequence that actually gets processed. Third, the context window, the hard token limit that constrains how much conversation history the model can see at once, and that forces you to think carefully about truncation and memory strategies. When you write a system prompt, think in 3 layers. Personality defines the voice and style, formal or casual, enthusiastic or measured, expert or approachable. Behavior defines what the model should do, what tasks it handles, what output format it uses, how it handles ambiguous requests. Constraints define what the model should not do, topics to avoid, formats to reject, boundaries to maintain. A system prompt that covers all 3 layers clearly and concisely will produce far more consistent model behavior than one that only addresses 1 or 2. Lesson checklist. Before moving on, Make sure you can articulate the difference between a base model and a chat model without looking at your notes. You should understand the role of each message type, system, user, assistant, and why that structure matters for training. You should know what a chat template does and why using the wrong one causes problems. You should be able to apply a chat template in code, format both single-turn and multi-turn conversations correctly, and run a basic inference test to verify the output. If any of those feel shaky, this is the moment to go back, because the next lesson, where we build actual training datasets, assumes all of this is solid. Key takeaways. Willis izan. Din ezinam Willis izan practice. You'll master these techniques quickly. 6 things to carry forward. Chat models are instruction-tuned base models. Same architecture, different training. The messages format structures every conversation as system, user, and assistant turn. Chat templates convert that JSON structure into the model-specific token sequence the model actually processes. The context window is a hard token limit that encompasses the entire conversation, not just the latest message. System prompts are your primary behavioral steering mechanism. Use them precisely. And multi-turn conversations work by passing the entire conversation history as input on every single call. The model's memory is just the context window. What's next? You now have a complete mental model of how chat systems work, from the training pipeline that creates them, to the message format that structures them, to the templates that serialize them, to the context window that constrains them. The next step is building the data that will teach your model new behavior. Continue to lesson 5.2, preparing chat datasets. Additional resources. For deeper reading, the Llama 3.1 chat template documentation covers the exact token format we used throughout this lesson. The ChatML format specification is worth understanding as a comparison point. It's what many OpenAI compatible APIs use. The original instruction tuning paper from Wei et al. Is the foundational academic reference for SFT, and Anthropic's RLHF explanation is one of the clearest public descriptions of how preference optimization actually works. All of these are linked in the course materials. You're ready to build training data. This capability comparison chart shows something important. The differences between model types aren't uniform across all dimensions. The base model scores well on raw text completion. That's literally what it was trained for. But across instruction following, safety and alignment, and personality, it falls far behind the trained variants. The chat model and the RLHF trained model lead on instruction following and personality, while the RLHF model specifically pulls ahead on safety and alignment. The instruct model sits in between, better than base at everything, but not as polished as a full RLHF model. This chart is a useful reminder that better model isn't a single axis. It depends entirely on what you need the model to do. 3 instruction formats dominate the fine-tuning landscape, and knowing how they differ will save you from subtle bugs. The alpaca format uses plain text labels, hash, hash, hash instruction, hash, hash, hash input, hash, hash, hash response, with no special token. It's simple and human readable, but models have to learn from context where each section starts and ends. ChatML introduces structured tags like im_start and im_end with role identifiers, giving the model explicit boundaries to condition on. Llama 3 uses a similar approach but with its own token vocabulary: begin_of_text, start_header_id, EOT_id. The critical rule: always use the format. Mixing formats is one of the most common sources of degraded fine-tuning results, and it's entirely avoidable. This breakdown of system prompt components gives you a practical template to work from. Role definition establishes the model's persona: expert bot or Python tutor or whatever fits your application. Behavior rules specify how the model should respond. Use code examples. Ask clarifying questions. Explain your reasoning. Knowledge constraints scope what the model draws on. Focus on Python 3.11, prefer the standard library. Output format tells the model how to structure responses, Markdown, JSON, prose, or a specific template. Safety and guardrails define what the model should decline, and tone guidance sets the interpersonal register: professional, friendly, formal, casual. A system prompt that addresses all 6 of these components will produce dramatically more consistent behavior than one that only covers 1 or 2. The performance gap between base and chat models is most visible on task-based evaluation. On the bar chart, tasks like write a poem about Python and explain gradient descent show the largest gaps. These require the model to interpret an instruction and produce a structured response, which is exactly what chat models are trained to do. The radar chart adds nuance. Chat models outperform base models on staying on topic, following instructions, and producing useful output formats. But the base model holds its own on raw fluency. This is why you don't fine-tune a base model for a chat application. You start with an instruct model and refine from there. The full fine-tuning pipeline has a clear shape. You start with a pre-trained base model. You run supervised fine-tuning on chat data, instruction response pairs that teach the model conversational behavior. That produces an instruct model. Optionally, you then run preference optimization, DPO or similar, using preference pairs where human rate is indicated which of 2 responses they preferred. That produces a chat model tuned not just to follow instructions, but to produce responses that humans actually find helpful and appropriate. In this course, you'll be working in the SFT stage. Understanding the full pipeline helps you know where your work fits and what the next steps would look like if you wanted to go further. The choice between SFT and RLHF-based approaches comes down to resources, requirements, and use case. SFT trains on correct completions. You provide the right answer, the model learns to produce it. It needs between 1,000 and 50,000 instruction pairs, runs at relatively low cost, and works well for task-specific fine-tuning. RLHF trains on preference pairs. You show the model 2 responses and indicate which is better, and requires human annotation at scale, which makes it medium to high cost. The payoff is better alignment, calibrated safety refusals, and responses that more closely match human preferences. For building a general-purpose assistant, RLHF is worth the investment. For fine-tuning a model to perform a specific task reliably, SFT is the right tool. This comparison makes a point that's easy to underestimate. Data consistency is not a nice-to-have, it's the single biggest lever you have over fine-tuning quality. The inconsistent dataset produces correct format responses only 40% of the time, with the remaining 60% split across wrong tone, missing sections, and wrong length. The consistent dataset hits 88% correct format, with errors reduced to a small fraction. The model didn't change between these 2 runs, only the training data did. When you build your datasets in the next lesson, format consistency is the first thing to get right. Every example should follow the same structure, use the same role labels, and apply the same chat template. That consistency is what the model learns from.